In this video, we're going to start a new topic, and that's general vector spaces. We've already seen an example of one vector space, and that's Euclidean space. Now we're going to see how the things that we've defined in Euclidean space, like subspaces, linear independence, spans, can be extended to a much more general setting. A fundamental operation that we've talked about for vectors in Rn is that of taking linear combinations. So if we have k many vectors in Rn, v1 through vk, we can form this linear combination by multiplying vi by some real scalar ai and taking the sum. It was this definition of linear combinations that led us to define a subspace, which was just a non-empty set that is closed under linear combinations, defining the span of a set of vectors, which is just the set of all linear combinations of those vectors, and defining the concept of linear independence. We can look at linear combinations of many other kinds of mathematical objects. For example, we've already talked a little bit about taking linear combinations of matrices. We know that we can add matrices together, we know that we can multiply a matrix by a scalar, so we can also take linear combinations of matrices. Also for real-valued functions, we can take the sum of two functions, we can multiply a function by a scalar, and we can take linear combinations of functions. Another example would be polynomials. We can add polynomials together, and we can multiply polynomials by scalars. So in all of these cases, we can define linear combinations. And moreover, linear combinations of these kinds of objects behave a lot like linear combinations of vectors in Rn. What that means is that a lot of the theorems that we've already shown can be extended to all of these situations. That's because the operations of addition and multiplication by scalars are well behaved. They follow certain nice rules, the same kind of rules that addition of vectors in Rn satisfy. So once we have these definition of linear combination of these objects that satisfy certain rules, then we can again define subspaces, spans, linear independence, and a lot of the results that we've already shown for Rn carry over to all these other settings. So that's really the nice thing about a general vector space, is that once you have this definition, you can just show a theorem about a general vector space. And then once we verify that matrices form a vector space, real-valued functions form a vector space, polynomials form a vector space, then we can automatically get that these general theorems apply in each of these specific situations. So let's go ahead and look at what conditions we need for something to be a vector space. So we start off with some non-empty set V, on which we have operations of addition and scalar multiplication defined. Now the words addition and scalar multiplication here are chosen to remind you of the case of Euclidean space, how we add vectors and multiply vectors by a scalar. However, the important thing is that the operations of addition and scalar multiplication satisfy all the conditions that I'm going to give next. So we'll actually see an example where addition is defined in quite a strange way. It doesn't look anything like usual addition. However, it still satisfies all the necessary conditions, so we can still define a vector space with that notion of addition. And most of the examples that we'll look at, things like vector spaces of matrices, functions, polynomials, addition and scalar multiplication will be quite natural. So there's actually 10 conditions needed for something to be a vector space. So it'll take us a little bit of time to go through them, but most of them are quite natural. The first condition is closure under addition. So this is very similar to the condition that we saw for something to be a subspace in the case of Euclidean spaces. Closure under addition simply says that for every pair of elements in V, the sum x plus y is also in V. The second condition closure under scalar multiplication is also very similar to what we saw in the definition of a subspace. This says that for every element x in V in scalar C, which is just a real number, the element C times x is in V. So again, these two conditions taken together mean that the linear combination of any set of elements of V will again be in V. Now we also want that the operations of addition and scalar multiplication are well behaved, that they satisfy certain nice conditions. So for addition, we want it to satisfy the following conditions. The first is that it's commutative. So that means that for every two elements x and y in V, x plus y is equal to y plus x. As we go through these conditions, maybe you want to keep in mind a couple examples. For example, the case of an n-dimensional vector. The addition of n-dimensional vectors is commutative. Maybe also keep in mind the example of matrices. So matrix addition is also commutative. The second condition is that addition is associative. So that means that if we first take x plus y and then add z, that's the same as if we first add y plus z and then add x. So this is saying that in general, if we have a sum of several elements, we don't need to use parentheses. It doesn't matter in which order we add things. So again, this is something that's true for vector addition for n-dimensional vectors, real vectors, or in the case of matrices. The third condition is the existence of a zero element. So that means that there's some element in V that we're going to denote by this boldface 0 that has the property that under addition, it doesn't change what it's added to. So x plus 0 is equal to x for all x in V. So in the case of Rn, the zero element is just the all zero vector, right? The vector where all coordinates are 0 has this property that whenever we add it to anything, it doesn't change what we add it to. In the case of matrices, the zero element would just be the all zero matrix, the matrix whose every entry is 0. Now the last condition we have for addition is the existence of negatives. So this says that if we take x and we add it to x multiplied by the scalar -1, then the result is our zero element. Okay, so again, this is something that is true for n-dimensional vectors and also true for matrices. Okay, now we have some conditions on scalar multiplication. So we're going to say that V is well behaved under scalar multiplication if it satisfies the next 4 properties. So the first is again about associativity. So if we have some element x in V and we first multiply it by b to obtain a new element in V, and then multiply that by a, that should be the same as if we first just do the multiplication of real numbers, a times b, and then multiply that real number by x, our element of V. Okay, so we also don't need to use parentheses in scalar multiplication. That's what this condition is saying. We also want scalar multiplication to distribute over addition in V. So what that means is if we take any two elements of V, x and y, we add them together to obtain some new element in V, and then multiply that by the scalar a. That should be the same as if we first take x and multiply it by a, also take y and multiply it by a. So these are both, again, elements of V, and then add those two elements together. So those two things are the same. Again, this is something that we've used again and again in the case of n-dimensional real vectors, and we've also seen that this is true for matrices. The third condition is distributivity for scalar addition. So that means that if we first take a plus b, just the sum of these two real numbers, and multiply that by x, that should be the same as if we take a times x and b times x. So these are both elements of v, and then add those two elements of v. So again, these are just fairly natural properties, nice properties that we want scalar multiplication to satisfy. The final condition is that if we take the real number 1, that it doesn't change an element under multiplication. So for any element x and v, when we multiply it by 1, it is just x. Okay, so that's all the 10 conditions. So now we can actually define what a vector space is. So let V be a non-empty set that has some operations of addition and scalar multiplication defined. Then we say that V is a vector space if it satisfies the closure conditions, so it's closed under vector addition and closed under scalar multiplication. It's well behaved under addition, so it satisfies those 4 axioms that we saw for addition. And it's also well behaved under scalar multiplication, so it satisfies the 4 conditions we saw for scalar multiplication. So that is a vector space. In the next video, we'll look at some concrete examples of vector spaces.